Hi folks, I'm Pratik. We are the Tariff Warriors and today we are presenting our project, implementing and evaluating CRISP in Chamsim. Our goal was to tackle a specific high stakes bottleneck in modern processor performance. So, who is the opponent in this match? It's the memory wall. Modern out of order CPUs are incredibly fast, but they are constantly stalled by long off chip memory latencies, specifically from last level cache misses. Standard prefetchers are the great at guessing simple patterns like reading an array 1, 2, 3, but they fail at pointer chasing. Imagine an access pattern where address A contains the value of address B and address B contains address C. The CPU cannot know address C until it retries B. It's a serial dependency chain. This is exactly what happens in order book implementation in financial exchanges that use balanced search trees. The CPU ends up stalling and waiting for data. To understand our solution, think of a high stakes football match like the Champions League final shown here. In a match, 90% of a game involves passing the ball around, but there are a few critical moments, a breakaway run or a corner kick that actually decides the outcome. Modern processors are the same. Most instructions are just passing the ball. However, bottleneck instructions are the ones that decide the performance of the system. Our system, our solution, Chris, is about giving these match winning instructions the VIP treatment. First, identify. We find the bottleneck instructions causing the most delay. Then mark, we flag them as a critical task. Fast track. We change the scheduling logic to execute this critical task before others. Now, how do we implement this fast tracking? Think of a Sergio Ramos equalizer in the 93rd minute. Real Madrid was trailing and needed a specific critical intervention to save the game. Our implementation does exactly that for the CPU pipeline. It relies the three mechanisms. First is dynamic detection. We monitor loads at the retire stage to catch instructions that are stalling the team. Then second, backward slicing. When we find a delinquent load, we don't just blame that instruction. We track back to find its producers, the teammates who set up the play. Then prioritize the scheduling. Once identified, the scheduler stops doing first come first serve for everything and fast tracks the critical path. Now I will hand over the presentation to my teammate Anshuman.
Hi, I am Angshuman. Now let's get into the implementation. This flowchart is the heart of our implementation. I want you to focus on the feedback loop we built into the pipeline. Let's trace the life of an instruction here. Here you can see this is the dispatch instruction stage. When an instruction is dispatched, we check a new component called this critical PC table. If the program counter exists in this PC table, we immediately mark it as a critical instruction. And also we record at the same time the register dependencies in recent instructions so we can track who produced what. Next we move into the now we move on to the schedule or issue stage. This is where the magic happens. We split the ready queue into two, critical ready queue and non-critical ready queue. The critical issue logic ensures that if any critical instruction is ready, we move it directly to execution, bypassing all the older non-critical instructions. Now we move our focus to the retire stage. Here the instruction finishes and tries to retire. Here we ask, is this instruction a delinquent instruction? Meaning, did the latency exceed our dynamic latency threshold? If yes, the system triggers a backward slice mechanism. It traces back the dependency chain using recent instructions and updates the critical slice table. So the next time the specific code sequence enters the pipeline, the dispatch stage will recognize it and the schedule stage will fast track that particular instruction. To test this architecture, we didn't just use random code, we focused on pointer heavy workloads. We used traces from Spec CPU 2017. which was the exchange trace, and also two gap traces, BFS and SSSP. Additionally, we wrote our own scripts to generate traces for a reverse linked list and a limit order book. The reverse linked list was created to test our architecture under a light workload. Finally, the limit order book trace was designed to specifically simulate financial machine matching engines as mentioned in our problem statement. Now I pass over to my teammate Prasun.
Hi, I am Prasoon. Let's look at the results. Here we compare the baseline IPC in blue against our crisp IPC in red. At first glance, you might see marginal gains for standard benchmarks like BFS 14 or SSSP 14. This is expected because graph algorithms often have irregular memory accesses that are bounded by pure memory bandwidth rather than latency hiding. However, look at limit order book. We see a clear visual step up in the red bar. This chart makes it clearer. For general graph workloads, we see about 1% improvement, but for the limit order book trace, we achieved a nearly 5% increase in IPC. So why this difference? The limit order book trace is a classic pointer chasing scenario, traversing a balanced tree. Our backward slicing mechanism successfully identified the address calculation chain for the tree nodes. By prioritizing these calculations, we issued the memory loads earlier, effectively hiding the latency. While 5% might sound modest, in the context of high-frequency trading matching engines, a 5% throughput increase without changing the clock speed is a significant competitive advantage. To wrap up, similar to how Ronaldo scored in extra time to secure the 4-1 victory, Crisp secures performance in the extra time of memory stalls. Our three takeaways are: backward slicing works to identify critical dependencies in irregular pointer chases. Prioritized scheduling successfully transforms stalls into useful memory level parallelism. This hardware feedback loop specifically accelerates data-dependent structures like order books. We have effectively implemented the crisp papers strategy against memory latency, getting useful results. The code is available on GitHub. If you have any questions, feel free to drop an email to us. Thank you.
फाइनल शो फिगर फाइनल शो नहीं है क्या वो फिगर
Champions League final.
ओके 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 ओके
So to understand it.
टू अंडरस्टैंड आवर सॉल्यूशन
ठीक है, समझ गया ठीक है।
नाउ आई विल हैंड ओवर द प्रेजेंटेशन टू माय टीममेट अंशुमन। ठीक है ना?
सही है भाई, बढ़िया है।
तूने क्या कर डाला?
अरे रे गिर मत मुझसे।
मैं तो पीछे बैठा हूं क्योंकि मैं बहुत हिलता हूं।
बैठो।
ठीक है, आगे बढ़िया रहेगा, तुम आगे बैठो। मेरा हाथ पैर चुपचाप नहीं बैठेगा, यहाँ पे बैठूंगा।
ठीक है ना?
शाबाश बेटा, शाबाश।
शाबाश बेटा। ठीक है, हाँ बढ़िया। ये करो बेटा सुन, ये फंक्शन की और ये फंक्शन और ये वाला आगे पीछे हो जाओ, बिल्कुल करके हो रहा है ना, बस। नॉन इंस्ट्रक्शन, ओल्डर नॉन इंस्ट्रक्शन, फिर से बोलते हैं। now we move bypassing the older non instruction, यार नॉन क्रिटिकल इंस्ट्रक्शंस होगा ना,
धीरे धीरे आराम से।
Emotional damage.
ब्रो कैसा धीरे रिकॉर्ड करेगा?
Now I pass over to my teammate Prasun.
क्या हुआ भाई?
हर एक ट्रांजिशन पे किया है, ट्रांजिशन चल रहा है। कैसा है? और थोड़ा हाँ, चलेगा ना? हाँ ठीक है। तो भाई मेरा हर एक ट्रांजिशन
तो होता है भाई, मतलब समझाने में हो जाता है, होता ही है। थोड़ा सा उस साइड बैठो,
थोड़ा उधर जाओ, हाँ ठीक है ना?
We have successfully implemented the tariff.
यार तो कुछ और करना होगा, क्या बोलना है यहाँ पे? We have effectively
Implemented our strategy against.
we have effectively implemented the CRISP paper, CRISP 2017।
देख रहा है विनोद, अंग्रेजी बोल बोल के कैसे बात को घुमाया जाता है।
पूरा बोल दो, इसका
Crisp paper strategy.
Crisp paper strategy with
Against-
promising results. Yes, sir.
With promising results.
You can check our code at the given.
If you have any questions, feel free to email us.
email. डाल देते हैं भाई.
चलो.
comment.
Like, share, subscribe.